In this video, we learn how to find the maxima and minima of a function. Introduction. A function f is said to have a maximum value at x is equals to a and y is equals to b if there exists a small neighborhood of a comma b such that f of a comma b is greater than f of a plus h comma b plus k. A function f is said to have a minimum value at x is equals to a and y is equals to b if there exists a small neighborhood of a comma b such that f of a comma b is less than f of a plus h comma b plus k. The maximum and minimum values of a function are known as extremum values of the function or simply extrema. So in the below graph, if you see, the point A is the lowest in its own immediate neighborhood. At this point, the function is said to have a minimum value, and point B is the highest in its own immediate neighborhood. At this point, the function is said to have a maximum value. So a point at which the function attains the maximum or minimum values are called the turning points of the function. In the above graph, we have two turning points at A and at B. A maximum or minimum value of a function is not necessarily the greatest or the least value of the function in any finite interval. So there may be maximum or minimum values of a function in an interval can be many. If f of a plus h comma b plus k minus f of a comma b less than 0, then f of a comma b is maximum at a comma b. And similarly, if the difference f of a plus h comma b plus k and f of a comma b is greater than 0, then f of a comma b is minimum at a comma b. Now we'll go for the working procedure to evaluate maximum and minimum values. So step 1. Differentiate f of x comma y and find out dou f by dou x, dou f by dou y, dou square f by dou x square, dou square f by dou x dou y, and dou square f by dou y square. Now equate dou f by dou x equal to 0 and dou f by dou y equal to 0. By solving these equations for x and y, we get set of points, say a comma b. So we evaluate r as t, where r is dou square f by dou x square and s is dou square f by dou x dou y and t is dou square f by dou y square at these points a comma b. If the following conditions are satisfied, we get the maximum and minimum values. If rt minus s square greater than 0 and r is less than 0, then f of x comma y has a maximum value. And if rt minus s square is greater than 0 and r is greater than 0, then f of x comma y has a minimum value. If rt minus s square is less than 0, then we cannot find any minimum or maximum values. So we call such a point as a saddle point. If rt minus s square equal to 0, then further investigation is required. The points a comma b, which are the roots of dou f by dou x equal to 0 and dou f by dou y equal to 0, are called stationary points. So we get maxima or minima at these stationary points only. Now we'll move to the problems on two variables. Here in the first problem, I'm considering a function f of x comma y is equals to x cube plus y cube minus 63x plus y plus 12xy. So the given function we are differentiating with respect to x and y partially. So we get dou f by dou x 3x square minus 63 plus 12y and dou f by dou y equal to 3y square minus 63 plus 12x. And we will evaluate the second order derivatives also. Dou square f by dou x square is 6x, dou square f by dou x dou y is 12, and dou square f by dou y square is equals to 6y. To get the stationary points, we equate the first order partial derivatives to 0. So dou f by dou x equal to 0 and dou f by dou y equal to 0. So by equating them to 0, we get x square plus 4y minus 21 equal to 0, y square plus 4x minus 21 equal to 0. By solving these equations, we get x is equals to y and x plus y is equals to 4. So first we will substitute x is equals to y. Then by simplifying, we get x is equals to minus 7 and x is equals to 3. So we substitute in the second equation to get the y values. Y is equals to minus 7 and y is equals to 3. So we get a two stationary points here, minus 7 comma minus 7 and 3 comma 3. Again by solving the relation x plus y is equals to 4, we get two more stationary points, minus 1 comma 5 and 5 comma minus 1. So total we have here 4 stationary points. So at each of these stationary point we'll calculate r, s, t and rt minus s square and check the above conditions. At minus 7 comma minus 7, r is minus 42, s is 12 and t is minus 42 and rt minus s square is 1620. Here at this point rt minus s square is positive and r is negative. Then the function f of x comma y has maximum value at minus 7 comma minus 7. And at 3 comma 3 r is 18, s is equals to 12, t is equals to 18. rt minus s square is 180. Here rt minus s square is positive and r is also positive. Then f of x comma y has minimum value at 3 comma 3. And we'll check the similarly for next two stationary points also. At minus 1 comma 5 r is minus 6, s is 12 and t is 30. rt minus s square is minus 324. So here rt minus s square is negative. And at 5 comma minus 1 also r is equals to 30, s is equals to 12 and t is equals to minus 6. rt minus s square is equals to minus 324. Here rt minus s square is negative. So at these two stationary points we cannot get any extremum values. So move to the next problem. Find the maximum and minimum values of f of x comma y is equals to 2 plus 2x plus 2y minus x square minus y square. The given function is f of x comma y is 2 plus 2x plus 2y minus x square minus y square. Differentiate partially with respect to x and y. Dou f by dou x is 2 minus 2x. Dou f by dou y is 2 minus 2y. Again differentiating partially with respect to x and y. Dou square f by dou x square is minus 2. Dou square f by dou x dou y is equals to 0. Dou square f by dou y square is equals to minus 2. So to get the stationary points, equate first order derivatives to 0. So here we get x is equals to 1 and y is equals to 1. So we have only one stationary point. So at 1 comma 1 rt minus s square is 4 greater than 0 and r is minus 2 which is less than 0. So f of x comma y has maximum value at 1 comma 1. To get the maximum value of the function, substituting this function in the given function. So we get 4 is the maximum value of the function. Another problem on two variables. So examine the extremum values for f of x comma y is equals to 3x plus 4x cubed into y square plus 2y. Differentiate partially with respect to x and y, the given function. We get fx is equals to 3 plus 12x square into y square plus 2y. Fy is equals to 3x plus 4x cubed into 2y plus 2. And also the second derivatives will evaluate. F of x comma y will differentiate with respect to x two times. So we get fxx or dou square f by dou x square, that is equal to 24x into y square plus 2y, dou square f by dou x to y, 3 plus 12x square into 2y plus 2, and dou square f by dou y square is equal to 2 times of 3x plus 4x cube. So to get the stationary points, we equate the first order derivatives to 0, and by simplifying this, we get y is equals to 0, y is equals to minus 2, and x is equals to plus or minus 1 by 2i. Here we neglect the imaginary values of x. So for y is equal to 0, we get x is equals to 0 and x is equals to plus or minus root 3 by 2i. Here we consider only 0, 0. We neglect the imaginary values. And for y is equals to minus 2, we get x is equal to 0. So here we have two stationary points, 0, 0 and 0, minus 2. So at 0, 0, r is equal to 0, s is equal to 6, and t is equals to 0. So here we get rt minus s square is equals to minus 36, and r is equal to 0. And at 0, minus 2, r is equals to 0, s is equal to 6, t is equal to 0, and rt minus s square is minus 36. And r is equal to 0. So here 0, 0 and 0, minus 2 are saddle points. Now we'll move into the maxima minima for a function with three variables and connected with a constraint or a condition. Let f of x, y, z be a function of three variables x, y, and z, and these variables are connected by the constraint phi of x, y, z is equal to c. That is equation 1. So first we'll construct the Lagrangian function capital F of x, y, z, that is equals to small f of x, y, z plus lambda into phi of x, y, z minus c, where lambda is known as the Lagrangian undetermined multiplier. So to get the stationary points, equate dou capital F by dou x equal to 0, dou capital F by dou y equal to 0, and dou capital F by dou z equal to 0. So this results to dou f by dou x plus lambda into dou phi by dou x equal to 0. That is equation 2. Dou f by dou y plus lambda into dou phi by dou y equal to 0. That is equation 3. Dou f by dou z plus dou plus lambda into dou phi by dou z equal to 0, that is equation 4. Since the derivative of a constant is 0, so we are not considering that value. So solving 1, 2, 3 and 4 equations, we get x, y, z and lambda to get the stationary points of f of x, y, z. So here we consider a problem. Prove that the rectangular solid of maximum volume that can be inscribed in a sphere is a cube. Let 2x, 2y and 2z be the length, breadth and height of the rectangular solid. Let r be the radius of the sphere. Volume of the rectangular solid V is given by product of length, breadth into height. So V is equals to 8xyz, and equation of the sphere is x square plus y square plus z square is equals to r square. So if you see in the picture, this is sphere and we have inscribed as rectangular solid, and we have to prove that the rectangular solid is a cube. That means x is equal to y is equal to z. So differentiate the Lagrangian function. We get dou v by dou x plus lambda into dou phi by dou x equal to 0. That is, differentiating this with respect to the x, we get 8yz plus lambda times 2x is equals to 0. That is equation 3. Similarly, with respect to the y and with respect to the z, if you differentiate, we get equation 4 and equation 5. So from the equation 3, I can write 2 lambda x is equals to minus 8yz, or 2 lambda square, 2 lambda x square is equals to minus 8xyz. And similarly, from the equation 4 and multiplying with y, we get 2 lambda y square is equals to minus 8xyz. And from the equation 5, 2 lambda z square is equals to minus 8xyz. Since for all these quantities the right hand side is same, then I can equate 2 lambda x square is equals to 2 lambda y square is equals to 2 lambda z square, or x square plus y square and z square are equal. X square, y square and z square are equal, or x is equals to y is equal to z. So hence this rectangular solid is a cube, since all the 3 dimensions are same. So another problem is, a rectangular box open at the top is to have a volume of 32 cubic feet. Find the dimensions of the box requiring the least material for its construction. Let x, y and z be the length, breadth and height of the rectangular box. Volume of the rectangular box V is equals to xyz is equals to 32. Let f of xyz be the surface area of the rectangular box. Since the box is open at the top, we get f is equals to xy plus 2yz plus 2zx. So differentiating the Lagrangian function, we get dou f by dou x plus lambda into dou v by dou x equal to 0. So this results y plus 2z plus lambda yz equal to 0, and dou f by dou y plus lambda into dou v by dou y equal to 0. Then x plus 2z plus lambda xz equal to 0. That is equation 4. And similarly, dou f by dou z plus lambda into dou v by dou z equal to 0. That is 2y plus 2x plus lambda xz equal to 0. So solving 3 and 4 we get x is equal to y, and solving 4 and 5 we get x is equals to 2z. So the dimensions of the rectangular box are 4 comma 4 comma and 2. So these values we get if we substitute these values in equation 1. Find the shortest distance from the point 2 comma 0 comma minus 3 to the plane x plus y plus z is equals to 1. Let p of x comma y comma z be the point on the plane. Equation of the plane phi is x plus y plus z is equals to 1. Let d be the distance between the point P and the given point 2, 0, minus 3. Then f is equals to d square. This is the distance between the 2 points, x minus 2 whole square plus y square plus z plus 3 whole square. We get the equation 2. So differentiating the Lagrangian function, we get dou f by dou x plus lambda into dou phi by dou x equal to 0. That is 2 times of x minus 2 plus lambda equal to 0. And dou f by dou y plus lambda into dou phi by dou y equal to 0. That means 2y plus lambda equal to 0. That's equation 4. And dou f by dou z plus lambda into dou phi by dou z equal to 0. That is 2 times of z plus 3 plus lambda equal to 0. So solving these equations, we get x is equals to 8 by 3, y is equal to 2 by 3, and z is equals to minus 7 by 3. Find the volume of the largest rectangular parallelepiped that can be inscribed in the ellipsoid. The equation of the ellipsoid is given by phi of x, y, z is equals to x square by a square plus y square by b square plus z square by c square equal to 1. That is equation 1. And the volume of the rectangular parallelepiped is given by v is equals to 8xyz. Here the length, breadth and height of the rectangular parallelepiped is considered to be 2x, 2y and 2z respectively. So the Lagrangian equations can be given by dou v by dou x plus lambda into dou phi by dou x equal to 0, dou v by dou y plus lambda into dou phi by dou y equal to 0, and dou v by dou z plus lambda into dou phi by dou z equal to 0. So differentiating these things, so we get equation 3, equation 4 and equation 5. So 8yz plus lambda times 2x by a square is equal to 0. That is equation 3. 8xz plus lambda into 2y by b square equal to 0. That is equation 4. 8xy plus lambda into 2z by c square equal to 0. That is equation 5. So solving these equations, we get x is equals to a by root 3, y is equals to b by root 3 and z is equals to c by root 3. So by substituting these values, the volume of the largest rectangular parallelepiped v is given by 8 abc by 3 root 3. So thanks for watching this video. If you like this video, subscribe and look for some more videos on engineering mathematics. Thank you.